Okay, so today we're gonna start a new module. Let me share my screen. There we go. Okay, so today we're starting a new module. Remember that we're basically wanna try to cover the four main properties along the course. And today we're starting with the first one, right? And that's electrical properties. Hopefully we'll cover everything in 2 classes. So what's gonna be the agenda for this module? Quick introduction on electrical properties of materials. Then we'll compare the 2 main theories that dictate what electrical properties, or actually how electrons behave, and how those electrons or how those theories influence the acceptance of those concepts on the behavior of materials in terms of electrical properties. So we'll compare the classical and the quantum mechanical theory. Then we'll sort of briefly talk about electrical conductivity in metals, superconductivity, semiconductors, and then actually there's one point missing here, that's electrical conductivity in ceramics and polymers. So we'll see. Hopefully we'll get to superconductivity today, and then next class we'll cover semiconductors and electrical conductivity in other type of materials. So quick introduction. So we know that a lot of materials are capable of conduct electrical current, right? And that's actually one of the many types of classifications that we have for materials. If a material is able to conduct electricity, well, it's called a conductor. If it can conduct electricity, but it doesn't have a high electrical conductivity, that's a semiconductor, and then we obviously have the non-conductors or insulators, right? And we all know from your previous courses that actually, at least in metals, what controls electrical conductivity is electrons, right? This is not true for all materials. Remember when we were learning about ceramics, we learned that actually phonons have an important contribution there. But talking about metals and alloys, well, electrons are the main ingredient, if we want to call it. They are the main part in electrical conductivity, right? And especially those electrons that are far away from the nucleus, right? So that means outer or valence electrons. And that's why we're gonna use electron theory. So what we learn in the first module, we'll use some of those concepts and put them more of like a practical way of applying those concepts, and we'll see how they work and why what they mean. Okay. So what you see there is a table, well, if you want to call it a table, a graph, whatever you want to call it, where you can see the room temperature conductivities of the main 3 types of materials, right? Metals, semiconductors, and insulators, metals being conductors, right? And we can see that actually we have a huge range of values, and actually there's a huge difference in orders of magnitude, right? Metals can get up to 10 to the 6, whereas insulators can be as low as 10 to the negative 20. So we have a difference in orders of magnitude of about 26. And if actually we don't see here, but if we were to put here superconductors, that it's a a topic that we'll also briefly talk about. Well, that's orders of magnitude greater than metal. Superconductors can be in the order of 10 to the 18, 10 to the 20, up to 10 to the 24. So if we see the whole spectrum of conductivities, of values of conductivities in different materials, we can have up to a difference of 48 orders of magnitude. And that's huge, right? So as we can see, actually, electrical conductivity has a big variation from the one material to another. So that's just a quick introduction. And I also want to emphasize on this. These are some equations that we'll use, or that you might remember from your previous courses. So I just leave them there for your knowledge, so you can remember these equations. This is Ohm's law, right? I think you guys all learned Ohm's law. Potential difference equal to resistance times the electrical current, right? Another form of Ohm's law, current density, right? Relating current divided by the cross-sectional area of the conductor. So I guess, I mean, you guys have seen these equations before? Have you not seen any of these equations before? I guess that's the question.
Excuse me, Mr. What did you say?
If you've seen all of these equations before, or is there any equation here that you have not seen before?
Personally, I haven't seen many of them. I think I've only seen the first one in Physics 2, but the other ones I don't know.
Okay. Well, I guess we can cover them in the tutorial. We can go in depth. But just keep in mind that at least the first three that you see here, one second, these three, they're different forms of Ohm's law. Okay, this is potential difference, resistance current. Current density is current divided by the cross-sectional area. This is this is actually a tensor that I guess we can cover them in tutorial. Resistance is length, density, and cross-sectional area. Resistivity is the inverse of conductivity. This is resistivity. I guess the main equations we'll need, and we're gonna use a lot, is this one, okay, and this one. So J is basically the current density, and that is going to be quite important, right? And if you want to understand what current density is, it's basically this. So what the current density means is the current per cross-sectional area, right? That's what we call current density. This is the electric field strength times the conductivity. That's another way of expressing the electrical the current density. But okay, we'll talk, I guess, then we'll talk about these equations in the tutorial. But just keep them definitely in mind. We'll use them, and they're gonna be very, very useful. Okay, so let's gonna start talking about electrons, and let's sort of recall something we talked in the first module. So there are two ways to describe an electron. The first one is describe an electron as a particle, right? As usually, what we think an electron is, a particle, right? And we sort of talk briefly about this way of representing an electron, and this theory, what basically does is could explain the resistance of a material by means of the collisions of the drifting electrons with lattice atoms. So basically, electrons are moving. In that movement, they're colliding with each other, and they're colliding with lattice atoms. So the more collisions you have, the higher the resistance. The less collisions, so basically electrons moving, no collisions, the higher the conductivity. So that would be one theory, right? And this theory actually describes in a qualitative way the increase in resistance with an increasing amount of lattice imperfections. What do I mean by lattice imperfections? Grain boundaries, vacancies, dislocations, all those lattice imperfections. So it sort of makes sense, right? The more of those, the more lattice imperfections you have, the more collisions electrons will have with the lattice, and therefore the higher the resistance, right? Because electrons are not moving free. So that makes sense. And actually, this concept of particle, or this theory that describes an electron as a particle, it actually also describes or explains why the resistance increases with increasing temperature. Because we all know, okay, I increase the temperature, thermal energy increases, lattice atoms start to oscillate because remember, they become more mobile. So they start to oscillate about their equilibrium positions. And now, because they're not staying in a single position, but they're actually oscillating, it's more likely for electrons to go and collide with those atoms. And therefore, remember, the more collisions, the more resistance we'll have because electrons are not moving freely. So this theory actually explains well, in a qualitative way, why the resistance increases with lattice imperfections, which we all know that's true, and why the resistance increases with increasing temperature, and that also we all know that that is true. That's actually sort of a basic concept, right? The other way of representing an electron, and that's actually something we focus on a lot on previous module, is a wave. And remember, we were all talking about waves, and that's actually what I guess gave rise to quantum mechanics, right? So considering an electron as a wave gives us a lot of advantages, okay? And we actually think it's obviously a bit more abstract because considering an electron as a particle, it's a lot easier for our imagination, right? Considering an electron as a wave, it's a lot more difficult for our mind. But that's, I guess, a better approach. So the matter waves, the waves basically, may be considered or may be thought to be scattered by lattice atoms, right? So these waves of electrons, these electron waves, they are scattered by the lattice atoms. The atoms absorb the energy of the incoming wave. So all the lattice atoms, the atoms of the material, they absorb the energy of that wave, and therefore the atoms will start to oscillate. Once they start oscillating, they re-emit the energy in the form of spherical waves. And now what happens? If I have two or more atoms, these waves that are emitted, if they are in phase, or I actually have to consider, and remember Bragg's law, right? I have to consider whether those waves that are basically emitted as part of a reaction of the absorption of energy that the atoms had, if they are in phase, well, that wave will propagate with no problem. That wave will propagate freely, and that's what we consider an ideal crystal. So that wave doesn't suffer any change of intensity, any change of direction. So the electron wave passes without hindrance. That's coherent scattering. That's basically pure electrical conductivity. But if the scattering centers are not arranged, are periodically arranged, so that means if I have impurities, I have lattice imperfections, right? Vacancies, impurities, grain boundaries, dislocations, thermal vibration, everything. If I have that, the waves will be scattered, and then I have to see the phase relationship, right? And then obviously the wave will be incoherently scattered. There is no phase between one wave and the other. So one wave coming from one atom and the other, there's no phase relation. Then the wave is incoherently scattered. And then I have resistance. So it's obviously a more difficult concept. It's not as easy as saying, okay, I have a particle, the particle is colliding with an obstacle, and then yes, that's resistance. Here's a bit more involved, because I have waves that are scattered by lattice atoms. These atoms absorb the energy of the wave. They start to oscillate. They re-emit the energy in the form of spherical waves. And then I have to see whether those spherical waves are in phase or are not in phase. If they're in phase, then I have coherent scattering, then I have conduction. If they're not in phase, then I have incoherently scattering. There is obviously no phase relationship between the waves, and therefore I have resistance. Is it clear so far, guys? Sort of. I mean, it's basically something we already talked in previous module, but it's sort of a refresh on what we learned.
Yes, Mr. From this, I had a question because I remember we kind of saw this in phases transformation.
Yeah.
When we have the coherent interface between crystals, I guess, between grains. When they are coherent, even there's a boundary, then is the current evenly distributed, or it's still getting incoherently scattered?
No, I mean, if I have coherent interfaces, then there is a lot more chance that it's not going to be for every single case of waves, but if I have coherent interfaces, not only between grains, in general, if I have coherent interfaces, even if it's an impurity and the matrix, if it's a coherent interface, then there is a higher chance of the waves of the atoms being around that imperfection to be in phase. It's not 100% sure that it will be, but there is a higher chance, a higher probability, and remember, all this is about probabilities. Remember, there is a higher probability that their waves will be in phase.
Yeah. Thanks, Mr.
Okay. So, actually, let's then talk about. I already talked about this. I guess it's just a repetition. Anyways, so this is classical electron theory. The first way of considering an electron. That's classical electron theory, right? Having an electron or considering an electron as a particle, right? And remember, the more collisions, we already saw that. So that's classical electron theory. It works well, but it has its limitations, and we're going to talk about them. So if we talk about classical electron theory, and then we derive an equation for conductivity with this theory, then we'll find something like this. We might do the derivation in the tutorial, so bear with me. That's something we'll leave for later. And again, I don't want you to become mathematicians, so I don't care too much on you learning to derive every single equation in quantum mechanics and in mechanics in general. So when you see this equation, I guess you might know two terms of this equation, right? I guess two of the four terms you see in this equation might be familiar. Can you recognize any of the terms that you see in this equation? Can anyone recognize any of these equations?
E is the charge of the electron, and M
That's
is
great,
the
yes.
mass of the electron,
And
and
m is the mass of the
and
electron.
F is the number of collisions or free
Sort of.
particles.
It's actually the number of free electrons. That's why it's F. It's the number of free electrons per centimeter cube, or per unit volume, if I guess we want to be more specific. The number of free
And
electrons
tau
per unit. Sorry?
and tau.
Yeah. So tau is called the relaxation time. What's the relaxation time? I guess an easy concept, because if you go and look on internet, it's going to be quite difficult to understand the concept. But to me, tau is basically interpreted as the average time, because at the end, you know, everything has to be an average. The average time between two consecutive collisions. And why am I talking about collisions? Because remember, this theory talks about collisions between particles, electrons, and lattice atoms. So let's say you have a time 0, one atom colliding with an electron, with a particle, and then you have a time 3, another collision, and then at time 5 you have another collision, and at time 10 you have another collision. Then you take the average of the time between collisions, and that's the relaxation time. It's basically the time that, you know, the model is relaxed. That means there is no collisions. It's the average time between two consecutive collisions. Is the concept of the relaxation time clear? And is the concept of the number of free electrons per unit cube? I guess that's quite easy. Is the concept of the equation in general clear? You guys have any questions about that?
Can you repeat the N?
So NF is the number of free electrons per centimeter cube, or per unit volume, as you want to call it. Because remember, we're considering this model as a particle, right? As the electron is a particle. So we need free electrons. We need electrons that go and move freely in the lattice. That's basically enough, the number of free electrons per unit volume.
Thank you.
Okay. Now, if you see that equation, then what you can say about the conductivity, guys, with this theory, with the classical electron theory? What can you say about electrical conductivity? Just looking at the equation.
We can see that the more free electrons there are, it will be the easier for it to conduct electricity.
Okay, that's one thing. What else? That's perfect. One thing, right? The higher the number of free electrons, it makes sense, right? The higher the number of free electrons I have, the more electrical conductivity I'm gonna have, and that's perfect. I mean, that makes sense, because obviously if I have more free electrons are moving freely. Remember, that's the idea. Electrons moving freely, that's conductivity, right? So we all know that, and that makes sense. What else?
I think that the conductivity is related to the movement based on the equation that is on the right part.
Yeah, okay, and I
So I
mean,
guess L is the distance between the electrons moving really.
it's the mean free path. It's the mean free path. So yeah, it's basically the average distance. Okay, I'm going to explain that, but let me go to the relaxation time first, and then I'm going to go and I'm going to jump to this equation. So if we think about electrical conductivity related to the relaxation time, then what the equation is saying is that the higher the relaxation time, the higher the conductivity. Does it make sense? Yes, because remember, relaxation time is the average time between collisions. So if I have collisions, just to put numbers, that obviously the collisions don't happen in seconds, right? They happen in microseconds, or actually millis, I don't know, 1 million of a second. But anyways, so if you think about that, let's say if collisions are happening every 2 seconds versus collisions happening every 5 seconds, obviously electrons are moving more, or they have more time to move if I have a higher relaxation time. So it makes sense that the higher the relaxation time, the higher the conductivity. So it definitely makes sense. And now, if I wanna, because obviously it might be difficult to know, okay, what the relaxation time is. Well, then we have this equation on the right that actually relates or tells me how the relaxation time is related. So the mean free path, that's L that you see here. So the mean free path is basically the average distance over which a moving particle, in this case a moving electron, changes its direction. So yeah, it's basically the distance, if you want to call it. It's equal to, as we know, velocity times time, right? V is basically the drift velocity of the electron, and T, I already, well, it's not T, it's tau, it's the relaxation time. So time times velocity equals mass, right? That's, sorry, it equals distance. So that's, I guess, the easy way of seeing this equation, right? The mean free path, so the average distance over which the electron is moving which moves before changing its direction, equals the drift velocity of the electron times the relaxation time, so times the average time between collisions. Okay, that's classical electron theory. Any questions, guys?
Yes, I will say that based on the theory that resistance increases as there are more collisions, then having a bigger time of relaxation means that there are less collisions, therefore the current is better.
Yes. I mean, that's basically another way of putting this equation in words, but yeah.
Okay, thanks.
That's perfect. Okay. Now let's go to real physics. Let's go to quantum mechanical theory. So remember, in this theory, we don't see electrons as particles anymore. We consider electrons as waves in this case. So let's think of electrons, and let's actually focus on valence electrons, because remember, they are the important ones here. Valence electrons, when in equilibrium, they start moving randomly, right? There's no preferential velocity in any direction. And I mean, we can visualize this just plotting this. Just plot, if we were to plot the velocity of electrons in X and Y directions, this is called, sorry, the velocity space. All the points inside this sphere, inside the circle, whatever, well, actually this would be a circle in 2D. If we were to plot it in 3D, this would be a sphere. They're all the endpoints of velocity vectors. So that means every point inside this circle or inside this sphere, they're all endpoints of the velocity vector. So you can see there, for example, V1. Okay, so let's say velocity 1 of an electron. Okay, that's the velocity. Let's say I'm just going to put numbers, right? 2 in x and 2 in y. Then I have B2, I have negative 2 in x and negative 3 in y. Oh, sorry, and positive 3 in y. And so on. So I don't have, and electrons don't have any preferential velocity in any direction. They don't have. They're all moving in at different velocities, right? And all the points basically that we have inside this circle or sphere are just the endpoints of those vectors, of those velocity vectors. But the maximum velocity that the electrons are able to assume when t equals 0 is the Fermi velocity. That means the velocity of the electron when it has the Fermi energy. And that's why if we have an electron that has a velocity at the Fermi velocity, this Bf, that is actually what we call the Fermi surface, or if it will be 3D, then that will be the Fermi sphere. So this velocity space is defined by a maximum. And the maximum radius of that circle or a sphere is defined by the Fermi velocity, by Bf. And the Fermi velocity is nothing else than the maximum velocity that electrons can assume when they have the Fermi energy. Is that clear, guys, so far?
I got a little lost in this part where you say that all points inside the Fermi sphere are occupied. What does it mean?
That basically means that we have different velocities inside the Fermi surface. I have here, I have another velocity there, I have another velocity there, I have. So basically, what this is saying is that every single point inside this Fermi surface, being this Fermi surface either a circle or a sphere, I have plenty of different velocities of electrons there. And remember that basically all these points, so a point here, a point here, a point there, a point there, a point there, they're all just endpoints of the vectors. They're all just endpoints of vectors, of velocity vectors of electrons. They're all endpoints. So that's what that point is saying. It's just basically that inside this surface, this Fermi surface, every single point represents a velocity vector, a velocity of an electron. And that's why I'm saying everything inside this sphere or surface is occupied. Because basically every single point there represents an endpoint of a vector, of a velocity vector. So that means I have plenty, millions, billions, trillions of different velocities of electrons. But there is one condition that they have a maximum velocity that they can reach, and that's called the Fermi velocity. Is that a bit more clear?
Yes, mister.
Yeah. Now, so if we think, let me draw this. Let me just erase all this and now draw. Now, if we think, and just going back to that point, right? Every single point is occupied, and I have a vector here, and I have a vector, sorry, there. And if I have one here, then I have one there. I have one there, I have one there, right? So what's happening with the velocity vectors? They're all canceling each other because remember, I'm saying all the points inside the surface are occupied, all of them. So if I have a vector there, I know I have the opposite of that vector because every single vector is occupied. It's just like a Cartesian plane. And I have the 4 quadrants, so I know if I have an endpoint of a velocity vector there, I know I have the endpoint of the opposite velocity vector there. And if I have one there, I have one there. And so this and that one cancel each other. And that happens for every single pair of velocity vectors. When obviously the material of the system is in equilibrium, right? So there is no net velocity of electrons, right? We're all clear on that, right? So that happens at equilibrium. Is this concept clear, guys? Does this make sense?
Yes, in equilibrium, yes.
Okay. Okay, so now let's see what happens when I apply an electric field. So this is equilibrium, remember. Equilibrium, nicely, all velocity vectors canceling each other. Now, let's say I apply an electric field. If I apply an electric field, the Fermi sphere is displaced opposite to the field direction. So that means this is the field, right? That's the electric field, and it's saying, if you see the graph, it's pointing towards the left of the screen. So my electric field is applied, let's say there, or negative x direction. It's applied on the negative x direction. Then the Fermi sphere, if you see actually what it does is it moves towards the opposite end. So it moves towards positive x direction. So it moves to the positive end of the electric field, right? And that obviously happens due to the net velocity gain of the electrons, right? So this disturbance, right, causes, because applying an electric field, obviously no equilibrium anymore. So I disturb my system, electric field in one direction, then the Fermi sphere moves in the other direction. Fermi sphere or Fermi circle in this case, but at the end it's the same if we're talking about into the E or 3D. So now what happens? Still, I'm going to have most of the electrons, or sorry, most of the velocity, electrons velocities canceling each other, because just look at the gray area, right? The shaded area. Still have this, right? I still have that and that. I still have that and that. So I'm still going to have electrons, or sorry, electron velocities canceling each other. I'm still going to have that. Most of them are still going to cancel each other. But because I move my sphere, now I'm actually going to have some electrons uncompensated. And what I mean by uncompensated is just they're not going to have a pair, the opposite, to cancel, right? Because let's just think of this, right? Let's say I have an electron there. Oh, sorry, there. Now it's here. So look at the area in lines, right? That is basically highlighted with lines, or it's colored with lines. If you look at that, then I don't have the opposite of that, because I moved my sphere. So now the electrons that are actually in that area, that now I'm gonna color with blue. So the electrons that are now in this area, they're going to be uncompensated, or obviously the velocities of those electrons, right? They're going to be uncompensated, so they're not going to have the opposite, so that they're not going to cancel. Right? Well, are those electrons the ones that cause current? Are those electrons the responsible for electrical conductivity? So now let's actually compare them. In the classical picture, so in classical mechanics, one will assume that all electrons drift under the influence of an electric field. So that means once I put an electric field, all electrons will move with a modest velocity, all of them the same velocity. That will be classical mechanics. But if we go to reality, and that is quantum mechanics, it teaches us that only specific electrons, and what are those specific electrons? Only the electrons here, or the electrons that have these velocities, right? The velocities in that blue area, only those participate in conduction. And only those drift with high velocity, with a high velocity that is close, actually that velocity is close to the Fermi velocity. So now you can see that in order for an electron to participate in conduction, it actually must possess a velocity equal to or near the Fermi velocity. Is this clear, guys? Is the concept clear?
Yes, mister.
Okay.
V, I have a question. V is the potential.
The velocity.
No, that difference.
No, it's still velocity. This, you mean this, delta V, right?
Yes.
That's velocity.
Uh,
It's the difference in velocity from the from where it will be, right? The shaded area and the cross-hatched area. It's basically the difference in velocity from where it will be, right? And where it is at now because of that drift of electrons due to the influence of the electric field I apply. But it's still velocity. It's not, doesn't have to do with potential. Okay. Any other questions, guys? So, in general, for purposes of the class and for the purposes of quantum mechanics and for the purposes of describing electrical conductivity, one can safely argue that the mean velocity of electrons responsible for conduction can be approximated with or by the Fermi velocity. Okay? So now let's see the equations, right? So the current density is just the product of number of the electrons times the velocity of the electrons and times the charge of the electron, right? If we sort of modify this equation that remember it was at the beginning, we know that that velocity can become Fermi velocity, right? we can approximate that velocity with the Fermi velocity. The electron charge doesn't change. And what changes also is that now we don't see a normal n there. So now we don't see a number, the normal number of electrons. We actually see now an m prime. And if you see the m prime is just the number of electrons. This is not a product, right? It's just the number of electrons at the Fermi energy, at EF. And why is going to be that? Because remember that we're saying that conduction or electrons responsible for conduction are electrons that have the Fermi velocity. And we said that the Fermi velocity is the velocity that electrons assume when they are at the Fermi level, at the Fermi energy. So actually the n should be the number of electrons that are at the Fermi level or at the Fermi energy. Okay. Okay, so n prime will basically become the number of displaced electrons per unit volume. But if you want to, understand this concept, is actually the number of electrons that we have at the Fermi level times that difference, right, of energy. Okay. Now let's keep expanding this. So if I replace, I'm going to have the Fermi velocity times the charge of the electron times this part here, right? That, as I said, is basically the number of electrons at the Fermi level times the difference of energy, right? Now, how can I represent this delta E term? Right, that's this difference in energy. Well, it's just, remember this, dE times dk, right? So delta E actually becomes the differential of energy with respect to the wave vector times obviously the difference of the wave vector, right? And we keep replacing, right? Because we have here a velocity. Remember this term here. Sorry, this term here, we all know this term. You can go back to module 1, you can look at your equations, and you see that that term actually relates the reduced Planck's constant and the Fermi velocity. That's why you see now Fermi velocity squared. Well, just the velocity, right? That in this case, the velocity becomes the Fermi velocity. Okay. And now let's finish this. So, density with classical electron theory becomes this equation. Sorry, I forgot to highlight it. It's that equation. Why? Because now I can relate H with delta K. I can relate this with the equations I have at the beginning. We'll cover those equations in the tutorial. I can relate those equations, and I see that there is a relationship with the charge of the electron. There's a relationship with the relaxation time, and with the electrical field. And that we get at the end that the current density is this a bit complicated equation, right? Compared to the simple equation we had for the classical electron theory, it becomes a bit more involved, right? And this is, remember, this is just current density. Now I have to transform this actually into conductivity, right? Now, let's sort of understand this Okay, so I'm just copying the same equation. Look, same equation. And before we actually convert this, right? Before we actually, I guess, fully understand the concept of this equation, let's make another consideration. Let's say the electric field here in this case, right, points or is pointing in the negative kx direction, right? Because remember, all this is k space, right? Wave vector space, reciprocal space. Then I know that the components of those velocities or of the velocities that are parallel to the positive kx direction contribute to the electric field, right? Sorry, to the electrical current. So if I have components actually in y, right, or ky, they're just gonna cancel each other, right? So they don't contribute. So just the projections, basically, of the Fermi velocities in the x direction. They're the only ones that are going to contribute to the electrical current, because I have an electric field being applied in the negative x direction. So if I project this vector, the velocity, the Fermi velocity, or any other velocity vector there, if I project it, I know that the y component is going to cancel, and only the x is going to be the responsible for contributing, or the component in x is going to be the responsible for contributing to the electrical current, right? So I can basically transform that, and I can safely say that, well, that actually BFX becomes BF times the cos of that angle, right? The cosine of that angle. So let's just add contributions in the first and fourth quadrant. I don't need contributions in the other quadrants, right? So instead of calling it BF, I'm just gonna use the projections in the x direction, so it becomes BF cosine of theta times squared. That's the same, but now I'm gonna integrate for all those vectors from here to here. So from negative pi over 2 to pi over 2. And you all can do math, you all can integrate, and you will get to the point of this equation. That's just integration, that's just math. Now, that is for 2D. That is for a circle. If we go to real life, we have 3D materials, so I can do the same derivation, I do the same process, I integrate, but for a sphere, so for a 3D, and I'm gonna get this, it's the same, basically, just that, you know, we're talking about a sphere, we're not talking about a circle, so obviously now it's gonna be 1/3. But then all the other terms is going to be the same. And you can integrate, you can actually try this at home. You can do the same process, but now for a sphere, and you'll get that equation. Basically the same. Now, if we use the concept that current density, that's J, that current density is equal to the conductivity times the electric field. If we use that concept, then the magical equation appears. That is conductivity for 3D, right? If it will be 2D, then all it will change, it will be just 1/2 of that, right? Then everything will be the same term. So that the equation that you see highlighted there, that is the equation for electrical conductivity in considering the quantum mechanical theory. So we see now that the electrical conductivity again depends on the on the charge of the electron. It also depends on the Fermi velocity or the velocity. It also depends on the relaxation time. So these two terms are sort of, we have them from before, right? The relaxation time and the number of electrons at the Fermi level. Well, in that case, it was just the number of free electrons, remember? Now we have the number of electrons at the Fermi level. We had the relaxation time, but now we see there are other terms involved. And actually, there's one other term involved, and that is the Fermi velocity, right? And now, actually, we see that we don't have here in the equation, there is no presence of the mass of the electron. So there is a big difference, right, between this equation and this equation, right? You do see a big difference. And that is actually the most accurate equation for electrical conductivity in materials that depend on electrons for electrical conductivity. So that means in metals and alloys, right? Is this clear so far, guys? Okay, so this equation actually reveals then that the conductivity depends on the Fermi velocity, the relaxation time, and the population density. That's just the number of, I said, the number of electrons at the Fermi level per unit volume, right? But you can call it as you wish. It's just the number of electrons that are contributing to the conductivity, right? Times the Fermi velocity, and it makes sense, right? The higher the velocity, the higher the conductivity. The higher the relaxation time, the higher the conductivity. The higher the population density, the higher the conductivity. So it makes sense. It's actually a lot more meaningful than the classical electron theory, because it tells us that not all free electrons, so it's not longer, as I said, it's no longer NF, so it's no longer than all free electrons are responsible for conduction. It actually tells me that only those electrons that are at the Fermi level, so that's called the population density, or the electrons per unit volume over the number of electrons per unit volume that are near the Fermi surface. And that's why we spend a lot of time talking about or trying to get to that concept of the Fermi surface and Fermi level in the previous module. Because are the electrons that are there or near there that are actually contributing to electrical conductivity, and not all free electrons, as classical mechanics says. Is that clear, guys?
Yes, Mr. This is pretty much what we saw before.
Yeah, I mean it is related, and that's why we spend a lot of time building on those concepts, so you can I just sort of try to understand how the practical application of the concepts. Okay, let's go with let's actually go with the coffee break, please. Who was
Mr.
Yes, Jose.
This information is from the same book, Electronic Properties of Materials, or is from other book. This information.
It's a combination from two books, I believe. Yes, it's a combination from Solid State Physics.
Okay.
And from Electronic Properties. Yes.
Okay. Thanks.
Yes. You're welcome. Who's in charge of the coffee break today, guys?
My turn, teacher.
Okay, Julio, please go ahead.
Okay. Good morning, teacher. I said I have a topic. My topic I talk about the propagation of electrical trees in a polymer matrix. Okay. What's the problem in this case? A weak alternating current was passed through the decomposition channel of an electrical tree, and a small amount of alternating electrical quantity was present on the tip of the electrical tree, resulting in an intense local electrical field around the tip of the electrical tree. The emissions of electrons accelerate in the intense local electric fields, resulted in the decomposition of the polymer materials. Okay, what is the electrical tree? In electrical tree, in electrical technology, especially in the high voltage insulation field, polymer materials have been widely applied due to their excellent electrical, thermal, and mechanical properties. There are many kinds of polymer materials, such as polyimide, epoxy resin, polyethylene. The propagation of electrical trees in a polymer matrix is the typical pre-breakdown phenomenon. Leading to insulation failure, significant shortening in the lifespans of polymer materials in insulation applications. And what is the corona process? The corona process in polymeric materials has the objective of improving the permeability of the surface by increasing the energy and introduce polar groups into surface. And what is the solution? The solution is a composite materials, the polymer and nanoparticles, specific polyimide and titanium dioxide. The polymer materials around the nanoparticles was gradually decomposed in the corona process, leaving the nanoparticles behind the composition channels and on the surface of the composite matrix. The nanoparticles were gradually deposited and the decomposition channels of the electrical tree was eventually blocked, but by the deposit nanoparticles shutting off the alternating current in the decomposition channel. That is to say, the propagation of the electrical tree was restrained in the corona process, and improved corona resistivity was achieved for the PA and titanium dioxide composite material. The application is electrical aircraft and automotive. Thank you, Miss.
Thanks, Julio. Can you go back to the second slide, please?
This?
Yes. Can you explain this slide again and relate it to how basically how this new solution solves this problem?
Okay, I displayed the image. Okay, in the corona process, negative charge are distributed on the top of the projections and trapped in surface states. The formation in the engine's local electrical fields is oriented toward the top. According to quantum mechanical, the electrons may penetrate the potential barrier, emitting into the polymer matrix that the quantum tunnel effects. For this reason, the solution is blocked the enhanced the blocked enhanced local electrical fields, but because we need to improve the electric properties of the material polymeric materials.
Yes, how this new solution solves that problem? You just describe the problem. How this new solution solves the problem?
What is the solution?
You're defining the problem. You nicely describe the problem. How this new solution solves the problem?
The solution is the fields. Okay, in this case, the solution is polymate and nanoparticles, titanium dioxide in fields.
Yes. What do those titanium dioxide particles do? How do they interact? So you can solve this problem. That's my question.
The nanoparticles, so the fusion, the nanoparticle is blocked these local electric fields because the force around the tree formation tree, and this for this for
Okay. Thanks, Julio.
Okay, thank you, Messi.
Okay, person for next class. Brian, you're next, please.
Okay, teacher.
Okay, let's continue the class. Okay. I guess I forgot to explain this graph so you guys can sort of also relate. Why, for example, a monovalent metal, if you see this is population density, right, and that is related to the energy of electrons. And remember, so if you see a monovalent metal, they actually have the highest population density, right? And that's why monovalent metals So, and well, this is population density, meaning, electrons near the Fermi surface, right? So, in the valence band, we see, and you all know that monovalence metals have high conduction, so high conductivity. So, it makes sense. You can see here that the population density is highest compared to bivalent metals, for example. And the big problem of bivalent metals is, if you remember from previous module, you see in bivalent metals, you see that overlap in the valence band that obviously sort of blocks certain electrons, and that's why we don't have a high population density. And obviously, even don't talk about semiconductors or even insulators, right? That really have a small or really low population density, right? And that's why you see here the population density it's near zero, basically, right? For insulators. But yeah, that's just something I forgot to explain. So, okay. Now let's talk about electrical conductivity in metals and alloys, okay? And let's talk about pure metals first. So if we talk about resistivity of a metal, that remember resistivity is just the inverse of conductivity, so they're both related. If we consider the resistivity of a pure metal, call it copper, for example, and any metal actually, it will decrease linearly as I decrease the temperature. Right? So if I decrease the temperature, resistivity decreases, and obviously, remember, if resistivity decreases, conductivity increases, right? And we all know that. But resistivity won't decrease till zero. It actually it decreases up to a value that we call it residual resistivity, right? That's what you see here, res. It's just called residual resistivity. Then if we just consider this linear relationship, right? It's just resistivity at 0.2 is equal to resistivity at 0.1 times 1 plus the coefficient of thermal expansion times time temperature 2 minus temperature 1, right? So that's nothing. It's just, I mean, something you guys might know. It's just the linear temperature coefficient of resistivity, and that's just the difference in temperature, and that's the resistivity. I mean, that's quite simple. That's an easy concept, right? Now, if we think, right, or if we try to compare, especially the changing conductivity in light of the quantum mechanical concept or the quantum mechanical theory in the classical model, if we talk about number of free electrons, because remember that the classical concept defines number of free electrons as one of the elements in the theory, right? The number of free electrons will practically won't change with temperature. It will not change, basically. The number of free electrons, all electrons, it'll be basically the same with temperature. So it won't change that much. And now if we talk about the population density now, that remember we use that concept to define conductivity with quantum mechanical theory. It will also won't change with temperature, or it will change very, very lightly. But what will change is the mean free path, and that's the relaxation time. It will decrease with increasing temperature, as we might guess, right? If I increase the temperature, more atoms vibrating, more atoms are mobile, or the atoms become more mobile, and therefore there will be more collisions, and therefore the relaxation time will decrease, right, with increasing temperature. That makes sense. Therefore, I will have a decrease in conductivity, right? Thus, I mean, you can say, at least with pure metals, that both models work quite well, because they both have this dependence on temperature that is obviously very, very important in conductivity, right? So we can say that actually both models describe accurately the temperature dependence on resistivity, because both have the relaxation time term as part of the equations. And relaxation time is related to temperature, to the mean free path, and therefore we can say that both take into consideration this concept of electrical conductivity. Sorry, this dependence of electrical conductivity or resistivity, that's just the inverse, on temperature. But there is a difference. We already talked about the differences in general, and for example, considering all free electrons versus just considering the electrons at the Fermi level, and those are huge differences. Now we're just focusing on the difference in terms of temperature dependence on conductivity or resistivity, and they both work well in that regard. Now, if we talk about resistivity in general, right? I mean, the resistivity must have contributions, right, from different phenomena. So I increase energy, lattice atoms oscillate, incoherent scattering increases. Or if you want to call it the number of electron collisions increases, that also works for the classical theory. But there will always be this term, this residual resistivity term, and that term is quite important. So the residual resistivity is just basically the accumulation or the addition of different resistivities due to imperfections in the crystals. That is, for example, impurities, defects, and defects being vacancies, boundaries, dislocations, everything else. But there is this term that is the residual resistivity because of thermal energy. So this term is temperature dependent, slightly, and this residual resistivity is not temperature dependent. So the resistivity of a metal in general becomes or is composed of these two terms. The thermal resistivity, that is obviously dependent on temperature, and the residual resistivity, that is just the addition of, as I said, resistivity caused by impurities, defects, and defects being grain boundaries, dislocations, everything, whatever you want to call there. Those terms obviously don't depend. At least one can safely argue that they don't depend, even though you could argue, right, that wait, but if you increase the temperature, you might reduce the number of dislocations and therefore the resistivity will decrease. Yes, but that's sort of pulling pulling the rope too far. In general, we can say that the resistivity is divided or is composed by two main terms. A residual resistivity that basically comes from imperfections in the crystal, that is not temperature dependent, and from the thermal term that obviously depends on residual resistivity or resistivity coming from that thermal energy. That this formula is actually known as the Matheson's rule. That's just a rule that says, okay, resistivity is just equal to the addition of different resistivities. All of these processes are independent scattering processes, obviously, and all these processes are additive. That's, I guess, what Matheson's discovered, and it's nothing extraordinary, I believe. It's just adding independent or different and independent scattering processes, right? Scattering processes considering, remember, electrons as waves, right? And that's why we consider it scattering of waves. Okay. Now, let's see what happens with that residual resistivity, or in general, what happens with the resistivity as I go from a pure metal to an alloy. Do you guys think there is an influence of solute atoms in conductivity?
Mister, can you repeat the question?
This is just electrical conductivity in metals. So the resistivity in a pure metal basically depends on a thermal term, or a resistivity that depends on thermal energy, and the residual resistivity that comes from different imperfections. Now, do you think there will be a difference when I consider electrical conductivity in an alloy, considering that an alloy has solid atoms, right? That has other atoms. It's no longer a pure metal. Do you think the behavior of electrical conductivity will change, or the behavior of the electrons will change, and therefore the electrical conductivity will be affected?
In the class of heat transfer, I remember in alloys the thermal electric conductivity change.
Yeah.
I think
There will definitely be an effect of solid atoms, right? There will definitely be an effect of solid atoms. And actually, the resistivity of alloys increases with increasing amount of solid content. For example, you see copper there. If I put 1 atom percent of nickel in that copper, I see that the resistivity increases. And remember, if your resistivity increases, conductivity is decreasing. If I put 2 atom percent of nickel, resistivity increases even further. If I put 3, even more, and I can keep adding more and more, in this case nickel. Obviously there is a limit, but I can keep increasing the nickel content and I will have a higher resistivity.
And Mister,
Yes?
now is there a way that we can pour any other element in the alloy and make it go lower?
There are special cases, and I mean, in this case, we're talking about a metal that is a good conductor, right? Like copper. If I have an insulator or a semiconductor, that's why we do alloying. That's actually, putting other elements, you can call it alloying, for example, in semiconductors, so you can increase the conductivity and obviously reduce the resistivity. Yes, but we're talking about metals here, and in metals, especially metals that have high conductivity by themselves, if I put any alloy, it will, in general, most of them, it will cause the resistivity to go higher and therefore the conductivity to go lower. And there is obviously an effect that, different elements go or will alter the resistivity to different degrees. For example, let's actually go and show something. So this is silver, okay? And I guess that this is a better graph to explain. If I have silver, okay, if I put an element that has a valence of 2, like cadmium, then I can see that the resistivity already increases a bit. If I put indium that has a valence of 3, for example, right, even higher resistivity. Tin obviously has a valence of 4, even higher resistivity. Antimonium, valence of 5, even higher resistivity. And this is just comparing, right? Silver, a monovalent electron, a monovalent metal, a metal, you all know monovalent metals, high conductivities. How adding other elements, right? And especially look at that bivalent, trivalent, or a valent, or a metal that has a 4 or 5 as a valence. So that means valence electrons. Well, it decreases well, it increases my resistivity, so it decreases my conductivity. Right? And you can see here the effect, for example, for antimonium. You can see for silver, you know, the more the atom, the concentration of atomic percent, obviously the higher the resistivity, and that happens for all of them. And you can see that actually cadmium has the lesser effect, right? And that's because cadmium is only a bivalent metal compared to indium or tin, that, you know, they're 3-valent or 4-valent metals. So there is a shift, right, on the resistivity versus temperature curve if I increase my solid content, right? Now, does this agree with Matheson's rule? Does this agree with this rule here? Does it make sense? Because this is resistivity. Matheson's rule, what it says is that the resistivity arises from independent scattering processes, and all of these processes are additive. That's what Matheson's rule says. So does it make sense, or is Matheson's rule in accordance with what we see here? That the fact that I have a higher content of solute elements will cause, if I have higher content of solid elements, it will cause my conductivity, or actually my resistivity, to go higher, and therefore my conductivity to go lower. Does it make sense, guys? Or no?
Yes, because we will have more imperfections and more defects on the alloy.
Yeah, I mean, in general, you can say that impurities, right, goes higher, even though, yes, I mean, you usually wouldn't consider, let's say in this case, a copper nickel alloy. You wouldn't consider a nickel as an impurity, right? Obviously, because it's part of my alloy, so I wouldn't consider it as an impurity. But at the end, it's basically acting as an impurity. That I put it there on purpose because of something, being this increasing resistance, increasing I don't know, toughness, whatever. I put it there on purpose, but at the end, it is an impurity. So, and obviously that will also cause more defects and incoherence between, you know, different surfaces, and obviously this residual term will go higher, and it makes sense. Then the residual, the resistivity increases, and that's why you see that the residual resistivity is increasing, right? So this is for pure copper. If I have copper nickel 1%, then it will go here, my residual resistivity, and that's something important, right? This term is temperature dependent, but no solute dependent. This term is temperature independent, but it's solute dependent. So more solute I put, the more or the higher the residual resistivity. You know, I mean, that makes sense, right? You have a variation in the lattice parameter. Just by adding other material, the lattice parameter will change. There will be the scattering processes might be, or I will have probably more incoherent scattering processes. There will be also local charge induced, because if you remember, if I put, let's say, cadmium versus indium, I have a local charge of 2 versus a local charge of 3, so it changes, right? And even just having silver with cadmium, now I have a local charge that is also, or obviously influencing on a higher probability for scattering, right? And obviously having incoherent scattering, I mean. So it makes sense. Okay. I guess that's the important part. Okay, let's go now with this part. That's actually, I guess, the case, or the ideal case, for atoms that are all diluted, right? Now, let's think of atoms, how they're distributed in the solvent, right? They really don't have a specific order. They're usually randomly distributed. If that happens, and that's usually the case when I have a random distribution, I might not have, let's say, for example, if I have a 50-50 alloy A and B, where they alternately occupy successive lattice sites. So I have A, B, A, B, A, B, A, B, and all of them perfectly distributed. Then that's not a random distribution, but we all know that that might be a bit complicated to obtain, right? I might get it, definitely, but it's usually a bit difficult to obtain. But yes, I can get definitely a nice order of atoms, and I can have a random distribution of solid atoms. And if I see just looking at the graph, I see a difference between alloys, in this case a copper gold alloy, where I have a random distribution and where I have a specific order of atoms. If I have a random distribution, the number of centers where incoherent scattering occurs increases proportional with the number of substitutional atoms. And that makes sense. So if I have pure copper, no resistivity, not a lot of incoherent scattering, pure gold, the same. If I have 50-50 copper gold 1-to-1 atomic ratio, look at that, highest resistivity, because this concept here, and it makes sense. The number of centers where incoherent scattering occurs increases proportional with the number of substitutional atoms. So if I have a 1-to-1 atomic ratio, I have a high number of substitutional atoms. Therefore, and even according to Matheson's rule, I have a lot of incoherent scattering processes, and that gives me a high resistivity. Again, I'm talking about the disordered state, right? Just random distribution. And also, that's why I see if I have a 3-to-1 atomic ratio, right? So 3 parts of copper, 1 part of gold. I have a higher resistivity compared to having pure copper or pure gold, but it's also lower than having 1-to-1 atomic ratio, right? So it makes sense. Here I obviously have more solid atoms, let's say gold. So I have more solid atoms, higher resistivity. More solid atoms, but less than obviously in a 1-to-1 atomic ratio, higher resistivity. So it makes sense. It goes according, or it's basically aligned with what we learned. Now, what happens if I have a periodic arrangement? It's difficult to get, yes, but I can get it. And we know of many alloys that have a perfect arrangement of atoms. If I have an order matrix in solid, or a nice order between solid atoms and the matrix, then my microstructure will not be disordered, right? What happens? Then I have a periodic arrangement, so I have the nice AB, for example, or the ABC. Then those electron waves will be coherently scattered. Even though I have solid atoms, because of that arrangement, and this also answers, I guess, part of your question, Fernando, when you said, is there a way to decrease the resistivity? Well, to decrease up to the point of going lower than the actual metal, no. But at least I can go near that resistivity if I get an order microstructure. And you can see when it's ordered, you see there is actually a decrease in resistivity, right? It deviates from that disorder state that, it will predict a high or an increase in resistivity. It actually deviates because I have an order microstructure. Then when I get to that point, an order microstructure of, let's say, a 3-to-1 atomic ratio of copper to gold, then I actually have a decrease in resistivity and therefore an increase in conductivity compared to this, right? Not really higher than having pure copper. That will be difficult, but definitely compared to having a disorder arrangement of copper and gold atoms. The problem is that not all alloys show this tendency for long range ordering. It's only because, yeah, you can say, oh, it's ordered, but maybe just in one part of the material of the let's say part of crystal, but then everything else is disordered. So that's not useful. It actually has to be a long range order. So this arrangement has to really to be periodic. And if I have that, then yes, I will have this effect. But again, there are only few alloys that have that tendency, right? And among those are the ones you see there: copper gold, or copper 3 gold, gold 3 manganese. So those are the alloys that show it. There are more obviously, but it's quite difficult to get this tendency of alloys towards long range ordering. Okay. Now, from what you've learned, guys, how do you think you can get maybe not a fully ordered state, but let's say an ordered state, not fully ordered and nicely distributed perfectly, but how could you get sort of a nice order?
When having elements that have the same structure.
Okay, that's one option. Yes, elements or alloying elements that have the same microstructure. Okay, that's one thing. Nice. What else? I guess I'm gonna put my question in other terms. How can you get the same alloy, right? Copper gold, same example here. In what case will you get a disordered copper gold alloy? And in what case will you get an ordered copper gold alloy? Because it's the same, it's copper gold. I don't change anything in terms of composition. What will you change to get a disordered state, and how will you get an ordered state? Think of what you've learned so far in your other courses.
I think that it might be related to heat treatment.
It is
No.
related to heat treatment.
I mean, not exactly a heat treatment, but the cooling.
Well, and the cooling is the heat
So I
treatment.
mean,
Actually,
okay, there will be
go,
some sort of segregation in the material, so that will be a disordered state, I guess.
yeah. So, actually, yes. I mean, if let's say this material, right? If you anneal the material slightly below the order disorder transition temperature, because alloys that present this order disorder behavior, they have a transition temperature. If you anneal slightly below that temperature, then you will get an order state. And obviously, that annealing has to go accompanied with moderate cooling. Whereas if you quench the material, so you do a rapid cooling, then obviously you will get a disorder state, right? So yeah, it's related to how you heat treat the metal, the alloy. Perfect. Okay. Superconductivity. Superconductors are those materials that whose resistivities become immeasurably small. That one can consider them as zero. Once we get a critical temperature, the problem of that critical temperature is that it's usually quite close to 0 Kelvin, to the absolute zero, right? And we all know that it's quite difficult to get there. But that's actually what superconductivity is. So superconductors, and that's why they're called superconductors, because they basically have zero resistivity below that critical temperature. Once I go above that critical temperature, superconductivity is lost. So we have different superconductors, right? And with time, a lot of new superconductors have been discovered. The first superconductor discovered was mercury. That's where everything began, actually. They had to go to 4 Kelvin, and they saw the superconductivity effect on mercury. Then they saw it on tungsten at literally zero, at the absolute zero. And then, a lot of different materials were discovered until the more familiar ones that you actually know now, because of you all took ceramics. Remember this? The YbCO superconductors. So now we have metals, we have ceramics that have been found, or that have been synthesized also, to possess superconductivity. And obviously, I mean, when they discovered mercury, they said, okay, cool, but isn't it too difficult to get to 4 Kelvin, right? And so that's why they started to synthesize, especially ceramics, and all the ones you see here, all of these are ceramics. Right? All these are ceramics. And obviously they started to synthesize this. And why? What was the motivation? Because the temperature is a lot higher. Well, not a lot higher, but at least it's not really close to zero, to the absolute zero. Yes, it's still cold, quite low, 92 Kelvin, 100 Kelvin, but it's not as low as 4 Kelvin, 0 Kelvin. That's extremely low, right? So that's why the interest of synthesizing this type of superconductors that are actually ceramic superconductors, right? Because they have a higher critical temperature. Now, if we think of superconductivity, we know that it is quite useful, right? We want them on electromagnet, like RMI, like resonance imaging devices. We need them for high energy particle accelerators, for electric power storage, for transmission lines, power transmission lines, for the trains in Japan, for example, for fast computers. We saw some uses of some applications of superconductivity, right, in last semester. So it obviously it's quite important for a lot of applications, obviously high tech or high engineering applications. But it's quite important, right? And that's why we're gonna talk a bit about superconductivity and the theory behind superconductivity. These superconductors actually have 10 to the 16 times or a difference of 16 orders of magnitude than copper. We all know copper is an excellent electrical conductor, but a superconductor can have 16, 20 orders of magnitude higher than copper. So huge. And obviously, but that themselves, right? If we have them at room temperature, like for example, mercury at room temperature has a very poor conductivity. But if you put it at 4 Kelvin, it will have an extremely high superconductivity, 10 to the 16, 10 to the 17 times greater than. And so this state of superconductor is really, or has really to be considered by separate, because it's quite complicated. The theory is not fully developed, even though there are 4 theories. There's one that is mostly accepted, that's called the copper pair, and we'll talk slightly about that next class. But yeah, it's definitely a state by itself. As you consider solid, liquid, gas, I think superconductor, even though it's not really considered as a state, in the purposes of studying and approaching how superconductivity develops, it is really considered as a separate state. And so, again, as I said, this is why the interest of this type of ceramic superconductors, right? Because we don't have to go really low. We don't need liquid helium, for example, that has a boiling point of 4 Kelvin. We don't need liquid helium. We don't need liquid hydrogen to get superconductivity. We don't need to cool the materials in those liquids to get superconductivity, right? Because we don't need to go that low. Okay. So if I want to eliminate superconductivity in a material, obviously I can increase the temperature. That's something we all know. But there's another way to eliminate superconductivity in a material, and that is by subjecting the material to a strong magnetic field. And there's actually, such as there is a critical temperature to eliminate superconductivity, there is a critical magnetic field strength above which superconductivity will be destroyed, and that's actually called Hc. So that's the critical magnetic field strength above which I lose superconductivity in a material. But this critical field, magnetic field strength depends on temperature. And in general, if you see this equation, the lower the sample temperature, the higher the critical field. If this is lower, I have a higher critical field. And this is the important thing. Ceramic superconductors, unfortunately, usually have a very small Hc compared to metallic superconductors like tungsten, right? That's why they're very vulnerable to lose superconductivity. Even if I have a moderate magnetic field, so even if it's not strong, they will lose, or they tend to lose, that superconductivity just because of that strength. So ceramic superconductors, and that's the big problem of ceramic superconductors, and that's why everyone wishes there will be more metallic superconductors. The problem is we have to go really low temperatures, and that's not useful for practical applications. So that's the interest on ceramic superconductors. The problem, though, is that they have a small Hc. So superconductivity is not eliminated only by increasing the temperature, but also by reaching a critical magnetic field. Okay. I guess I'm gonna. Yeah, I guess I'm gonna stop there, and we'll continue next class. Any questions, guys?
No, mister. Everything has been clear.
Okay. Okay. I'll see you next class then. Thanks for reaching out. Remember actually I'll see you on Wednesday. Remember on Wednesday you have a tutorial, and you will have your lesson. Yeah, it's not a quiz. Yeah, you'll have your lesson at the end of the tutorial.
Hey, mister, what we saw today is going to a lesson also or not?
Yes, it will be there. Yes.
Okay.
Everything up to today will be part of the lesson. Yes. And hopefully we'll finish next class module 1, so that the exam, the first exam, will cover both modules, the introduction module and module 1. Yes. Okay. Any other question, guys? Okay. See you on Wednesday then. Take care. Have a good day, guys.
You too, mister. Thank you.
Bye, teacher.